Imagine a force so immense that not even light can escape its grasp, a cosmic entity that bends and warps the very fabric of space and time. We are about to embark on a fascinating journey to explore the birth of the most enigmatic objects in the universe, black holes. These mysterious phenomena have captured the imagination of scientists and dreamers alike, leaving us with more questions than answers. What exactly are black holes, and how do they form? Today, we'll dive deep into the science behind these celestial monsters and uncover the astonishing forces that give them life. Prepare yourself, as this journey will take us to the very edge of the known universe and beyond. Now imagine if we could take Earth and compress it down to the size of a marble. What would happen? Incredibly, Earth would become a black hole, an object so dense and powerful that it could devour the moon and much more. How is this possible, you ask? Today we will unlock the mystery behind the formation of these incredible cosmic beasts. From the final moments of massive stars to the formation of a black hole's infamous event horizon, we'll explore every step of their creation. But before we plunge into the depths of this cosmic journey, if you're as fascinated by the universe as we are, make sure to hit that like button and subscribe to Exploring the Universe for more mind-expanding content. Stars are not only the creators of light and heat in the universe, but they are also the cradles where the most mysterious objects, black holes, are born. To understand the creation of a black hole, we need to first explore the life cycle of a star. Stars form in colossal cosmic nurseries known as nebulas. These vast clouds of gas and dust, stretching across hundreds of light years, are the birthplaces of stars. Within these nebulas, pockets of gas and dust begin to collapse under their own gravity, forming dense regions called protostars. As the gas compresses, the temperature and pressure rise dramatically until nuclear fusion ignites at the core, giving birth to a fully fledged star. This marks the beginning of the star's life, a process that can take millions of years. Once nuclear fusion begins, a star spends the majority of its life in what is known as the main sequence phase. This is a period of relative stability where the outward pressure from the fusion reactions in the core balances the inward pull of gravity. Stars are essentially massive nuclear reactors, where hydrogen atoms are fused together to form helium, releasing immense amounts of energy in the form of light and heat. This process creates the radiation and stellar winds that keep the star's layers from collapsing under gravity. The larger the star, the more fuel it consumes, and the faster it burns through its life. A small star, like our Sun, can remain in this equilibrium for up to 10 billion years, while more massive stars live much shorter lives, sometimes only a few million years. The size of the star is crucial in determining its eventual fate. For a star like the Sun, the end of its life will be relatively peaceful. As it runs out of hydrogen fuel, the core will contract, while the outer layers expand, turning the star into a red giant. Eventually, the outer layers will be shed, leaving behind a dense, glowing core called a white dwarf, which will slowly cool over billions of years. This is the fate of lower mass stars, which will never become black holes. However, for much larger stars, those that are at least 8 times the mass of the Sun, the end of their lives is far more dramatic and catastrophic, leading to the formation of a black hole. Massive stars like blue giants live fast and die young. These stars burn through their nuclear fuel at an incredible rate, fusing not just hydrogen into helium, but also helium into heavier elements like carbon, oxygen, and even iron in their cores. Once the core of the star becomes dominated by iron, the fusion process can no longer generate enough energy to counterbalance gravity. Iron, unlike lighter elements, does not release energy when it fuses. Instead, it consumes energy. This is the tipping point in the star's life. Without the outward pressure from nuclear fusion, gravity takes over, and the core collapses in on itself within a matter of seconds. This sudden collapse triggers a supernova, an explosion so powerful that, for a brief moment, the star outshines entire galaxies. But while the outer layers of the star are blasted into space in this violent explosion, the core continues to collapse. If the remaining core is sufficiently massive, typically more than 3 times the mass of the Sun, it will continue to compress under its own gravity until it forms a singularity, a point of infinite density where the known laws of physics break down. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. This is the birth of a black hole. The star, once a beacon of light and heat, has now become a dark, invisible entity, warping space and time around it. The life cycle of a star, from its birth in a nebula to its death as a black hole, is a journey spanning millions or even billions of years. But for massive stars, the end is always dramatic. The formation of a black hole is the ultimate victory of gravity over the forces that have been resisting it for the star's entire life. What once was a massive ball of gas radiating light and energy has now collapsed into an object so dense that even light cannot escape its gravitational pull. It's a transformation that is both awe-inspiring and humbling, reminding us of the immense forces at play in the universe. When it comes to the life and eventual death of a star, mass plays the most crucial role. The mass of a star not only determines its brightness, size, and temperature, but also how long it will live and what its ultimate fate will be. In the universe, not all stars are created equal. Some are small and dim, living for billions or even trillions of years, while others are massive and bright, burning through their fuel in a matter of millions of years before meeting a violent end. The greater a star's mass, the more fuel it burns, and the faster it races through its life cycle. Essentially, the more massive a star, the shorter its lifespan. This is the fundamental reason why only the most massive stars can eventually collapse into black holes. Let's take our sun as an example. It is considered a medium-sized star, with a mass roughly 330,000 times that of Earth. The sun's mass allows it to maintain a relatively serene life, burning hydrogen at a steady rate for about 10 billion years. Currently, the sun is in the middle of its life, steadily fusing hydrogen into helium in its core, a process that provides the energy necessary to support its immense weight. When the sun eventually exhausts its hydrogen fuel, it will expand into a red giant, shedding its outer layers before collapsing into a white dwarf, a small, dense remnant of its former self. It will not explode in a supernova or form a black hole because its mass is simply not large enough to create the intense gravitational forces required for such a dramatic end. Instead, it will peacefully cool over billions of years. In contrast, the fate of more massive stars, such as blue giants, is far more turbulent. These stars, which are at least 8 times the mass of our sun, live fast and die young. Due to their immense mass, they burn through their nuclear fuel at a staggering rate. While our sun will live for billions of years, a blue giant may only live for a few million. These massive stars not only burn hotter and brighter, but they also produce heavier elements like carbon, oxygen, and iron in their cores. As they rapidly fuse these elements, the balance between gravity and the outward pressure of nuclear fusion becomes increasingly precarious. Once a massive star runs out of fuel, the core cannot sustain the outward pressure needed to counteract gravity. This leads to a catastrophic collapse of the core, triggering a supernova explosion, the most energetic event in the universe. But unlike smaller stars, which might end up as white dwarfs or neutron stars, blue giants often collapse into black holes. Their enormous mass creates gravitational forces so intense that nothing, not even light, can escape. These massive stars, particularly blue giants, are the mothers of black holes, giving birth to these cosmic entities through their own violent demise. The reason mass is so critical in determining a star's fate is simple: gravity. The more mass a star has, the stronger its gravitational pull. For smaller stars, gravity is countered by the outward pressure of fusion, allowing them to live long, relatively stable lives. But for massive stars, gravity becomes the dominant force, and once they exhaust their fuel, nothing can stop their collapse. This is why only stars above a certain mass threshold, typically around 3 times the mass of the sun, can form black holes. These are the stars that, after going supernova, leave behind a core so dense and with such a powerful gravitational pull that it creates a black hole. In the end, the mass of a star dictates everything: how bright it will shine, how long it will live, and how it will meet its ultimate fate. Smaller stars like our sun will fade away quietly, while massive blue giants will end their lives in spectacular explosions, leaving behind the most mysterious objects in the universe: black holes. The life of a star is a constant battle between 2 opposing forces: gravity, which pulls everything inward, and the pressure generated by nuclear fusion, which pushes outward. For millions or even billions of years, these forces remain in equilibrium, allowing the star to shine brightly in the cosmos. However, as the star ages and consumes its nuclear fuel, this delicate balance begins to tip. The star's core runs out of hydrogen, the primary fuel for nuclear fusion, and the star enters the final stages of its life. This is the beginning of the end, the moment when gravity, which has been patiently waiting, finally begins to take over. As the hydrogen fuel is depleted, the core of the star contracts under its own weight, and the temperature skyrockets. In smaller stars like our sun, the outer layers expand, turning the star into a red giant. But for more massive stars, the situation becomes far more dramatic. The star begins to fuse heavier elements in its core, like helium, carbon, and oxygen, in a desperate attempt to maintain the balance. This is only a temporary solution. Each successive fusion stage burns hotter and faster, but produces less energy, hastening the star's inevitable collapse. At this point, the core of the star has essentially become a massive nuclear furnace, operating in overdrive as it fuses increasingly heavier elements. The temperature in the core can reach millions or even billions of degrees, and fusion proceeds at a frantic pace. But as the star reaches the point of fusing iron, a critical juncture is reached. Iron is a unique element in the life of a star because it requires more energy to fuse than it releases. This means that the core can no longer generate the energy needed to resist the crushing force of gravity. The outward pressure that has been holding the star together disappears, and gravity wins the battle once and for all. The moment the core begins to fuse iron, the fate of the star is sealed. The nuclear furnace that has been burning for millions of years suddenly shuts down, and the star begins to collapse in on itself. Without the outward pressure from fusion, there is nothing left to counteract gravity. In a matter of seconds, the core implodes, collapsing under its own immense weight. The star's outer layers are pulled inward at incredible speeds, and the core is compressed to a fraction of its original size. This marks the beginning of a process known as gravitational collapse, an event so powerful that it can lead to the formation of a black hole. The collapse of the core is one of the most violent events in the universe. The temperatures and pressures within the star become so extreme that even the atomic structure of matter is crushed. Electrons are forced into protons, forming neutrons, and the core becomes a dense, neutron-rich remnant. For less massive stars, this might result in the formation of a neutron star. But for the most massive stars, the core continues to collapse beyond this point, and a black hole is born. In these final moments, the core reaches unimaginable densities, and the gravitational pull becomes so strong that not even light can escape. The outer layers of the star, meanwhile, are blasted into space in a supernova explosion, one of the most energetic events in the universe. But at the heart of the explosion lies the newly formed black hole, an object so dense and powerful that it warps the very fabric of space and time around it. The beginning of the end for a massive star is a spectacular yet tragic event. What was once a brilliant, shining beacon in the universe is reduced to a dark, invisible object, exerting its influence in ways we can barely comprehend. This is the fate of stars with enough mass to collapse into black holes, where the final moments of their existence mark the birth of something entirely new and extraordinary. The gravitational collapse of a massive star's core is one of the most cataclysmic events in the universe, a process so powerful and destructive that it reshapes everything we understand about physics. Once the star's nuclear fuel is exhausted and it can no longer support itself against gravity, the core implodes inwards at unfathomable speeds. This implosion is not just a gradual collapse, it happens almost instantaneously as the core's material is crushed under its own immense gravity. What was once a blazing furnace of nuclear reactions is now a compact, super dense object spiraling towards its final state. The core's collapse occurs at nearly the speed of light, compressing everything into an incredibly small volume in just a fraction of a second. In this moment, the forces at play are so intense that they bend and distort the very fabric of space-time itself. As the core contracts, the outer layers of the star are also pulled inward, and the entire structure of the star collapses toward its center. This rapid contraction creates a shockwave that blasts the outer layers of the star into space, resulting in a supernova, a violent explosion that can briefly outshine an entire galaxy. But while the explosion is incredibly energetic, the real drama is unfolding at the core, where a black hole is being born. As the core continues to collapse, it reaches a critical threshold known as the event horizon. This is the point of no return, the boundary around a black hole beyond which nothing, not even light, can escape. The event horizon forms because the gravitational pull within this region is so strong that it requires an escape velocity faster than the speed of light, which is impossible according to the laws of physics. Once the event horizon is established, the black hole becomes an inescapable prison for anything that falls within its grasp. Matter, energy, and even light are drawn in, never to return. What's extraordinary about the event horizon is that, from the outside, it marks the point where our understanding of the universe breaks down. Within the event horizon, all the laws of physics as we know them cease to apply. Time and space are warped to an extreme degree, and the singularity, an infinitely small, infinitely dense point, forms at the black hole's center. At this point, the star's core has been compressed to a volume with zero size, but infinite density, a concept so mind-boggling that even the greatest minds in science struggle to comprehend it. This is where a black hole's true power lies. In its ability to distort space-time in ways we can hardly imagine, the gravitational collapse that creates a black hole is not only a catastrophic event for the star itself, but also for the space around it. The gravity of the black hole bends light and warps space, creating gravitational lensing effects that can be observed from Earth. Despite being invisible, the black hole's presence can be detected through its effects on nearby objects, stars, gas clouds, and even light itself. In fact, this bending of light is what allowed astronomers to capture the first ever image of a black hole in 2019, providing direct evidence of the existence of these mysterious cosmic objects. In the final moments of a star's life, gravitational collapse marks the ultimate triumph of gravity over all other forces. The once luminous star is reduced to a dark, invisible point in space, a black hole exerting a gravitational pull so strong that nothing can escape. It's a process that defies our conventional understanding of the universe, a reminder of just how powerful and unpredictable the cosmos can be. If this cosmic journey is expanding your mind like the universe itself, why not help expand our channel as well? Don't forget to give this video a like and subscribe to Exploring the Universe for more adventures into the wonders of space. There's so much more to discover, and we're just getting started. Supernovas are, without a doubt, the most spectacular and energetic events in the universe. They mark the violent death of a massive star, releasing more energy in a few seconds than our sun will in its entire 10 billion year lifetime. When a supernova occurs, it outshines the entire galaxy in which it resides, briefly becoming one of the brightest objects in the universe. For a short period, a single supernova can outshine billions of stars combined, radiating incredible amounts of light, heat, and radiation across the cosmos. This extraordinary explosion signals the end of a star's life, but in doing so, it creates a lasting legacy that resonates throughout the universe. What causes this extraordinary explosion? As we've discussed, when a massive star exhausts its nuclear fuel, it can no longer sustain the outward pressure needed to counterbalance gravity. The star's core collapses in on itself, and this sudden implosion sends a powerful shock wave rippling through the outer layers of the star. These outer layers are blown off into space in a brilliant burst of energy, creating the supernova. The light from this explosion can be so bright that it becomes visible from Earth, even if it happens in a distant galaxy millions of light years away. In fact, some supernovae are so bright that ancient civilizations recorded them as guest stars, unfamiliar lights in the sky that shone for weeks or months before fading away. For a brief moment, the supernova is brighter than the combined light of billions of stars in its galaxy. This incredible brightness is the result of the immense amount of energy released when the star's core collapses. The explosion creates shockwaves that move through space at speeds of up to 30,000 kilometers per second, spreading the star's outer material far and wide. This debris, known as the supernova remnant, expands outward, carrying with it the elements forged in the core of the star during its lifetime. This is where the true legacy of a supernova lies, not just in its stunning brightness, but in the elements it leaves behind. One of the most remarkable aspects of a supernova is the creation of heavy elements. Throughout its life, a star fuses lighter elements like hydrogen and helium into heavier ones such as carbon, oxygen, and iron. However, the process of stellar fusion can only go so far. Heavier elements like gold, silver, and uranium require the intense conditions of a supernova to form. When the star explodes, these elements are created in the chaos of the explosion and are scattered across the universe. Over billions of years, these elements become the building blocks for new stars, planets, and even life itself. In fact, much of the matter that makes up Earth, including the iron in your blood and the calcium in your bones, was forged in the heart of a supernova billions of years ago. Supernovae are responsible for enriching the universe with the heavy elements essential for the formation of planets and life. Without these cosmic explosions, the universe would be composed primarily of hydrogen and helium, and complex life as we know it would not exist. The remnants of supernovae seed the universe with the materials necessary for the next generation of stars and planetary systems. In this way, supernovae are both a destructive and creative force in the universe, ending the life of one star while paving the way for new stars, planets, and potentially life to form. While supernovae are relatively rare events occurring only a few times per century in a galaxy like the Milky Way, their impact is immense. They serve as cosmic recycling centers, dispersing essential elements and reshaping the environments in which they explode. In some cases, the shock waves from a supernova can trigger the formation of new stars by compressing nearby gas clouds, jump-starting the process of star formation once again. The legacy of a supernova is not only in its breathtaking brightness, but in the heavy elements it creates, the new stars it inspires, and the life it makes possible. These cosmic spectacles are a reminder of the incredible power and beauty of the universe, where death and creation are intertwined in a never-ending cycle. The formation of a black hole is the final act in the dramatic life of a massive star. After the explosive death of a star in a supernova, what remains is an incredibly dense core. This remnant core, now stripped of its outer layers, is composed of highly compressed matter. In some cases, the core may collapse into a neutron star, a small yet incredibly dense object. However, for the most massive stars, the core continues to collapse under the force of gravity until something extraordinary happens. It becomes so dense that it forms a black hole. At this point, gravity becomes the dominant force, growing so intense that it overcomes all other forces of nature. This isn't just an increase in gravitational pull, it's a fundamental warping of the fabric of space and time itself. The core is now so dense that it begins to curve space-time, the invisible framework that shapes the universe. This curvature becomes more and more extreme as the core shrinks, creating a region where the gravitational pull becomes inescapable. What makes this process so mind-bending is that it's not just matter being drawn in, but light itself. Nothing can escape the pull of a black hole once it crosses a certain boundary. This boundary is known as the Hare event horizon, the point of no return. Once something crosses the event horizon, whether it's a particle of dust, a star, or even a beam of light, it is forever trapped by the black hole's gravity. Inside the event horizon, the gravitational force is so strong that the escape velocity, the speed needed to break free from the gravitational pull, exceeds the speed of light. And because nothing can travel faster than light, nothing that passes the event horizon can escape. This is why black holes are black. They do not emit any light, making them invisible to us except through their interactions with the surrounding matter. As the core continues to collapse, it eventually becomes a singularity, a point of infinite density where the laws of physics as we know them break down. The mass of the star is compressed into an incredibly tiny space, creating a gravitational force so extreme that even the concept of time becomes warped. The singularity sits at the center of the black hole, hidden behind the event horizon. Beyond this horizon, we can no longer observe or measure anything, making it one of the greatest mysteries in astrophysics. The birth of a black hole is not just a simple transformation, it's the creation of a region in space where the rules of the universe are bent to their extremes. Space is stretched, time slows down, and gravity reigns supreme. From the outside, the black hole appears as a dark void, but in reality, it is a region where immense forces are at work, shaping the fate of anything that ventures too close. As material approaches the event horizon, it accelerates and heats up, creating an accretion disk that often emits powerful X-rays and gamma rays. This glowing disk is one of the few ways we can detect the presence of a black hole, as the black hole itself remains hidden from view. For massive stars, the formation of a black hole is the ultimate conclusion to their life cycle. Once a source of light, energy, and fusion, the star's collapse gives birth to an object so dense and powerful that it challenges the very nature of existence. Black holes are the ultimate triumph of gravity over the forces that have fought to keep the star alive for millions of years. In their birth, they reveal the universe's most fundamental and awe-inspiring processes. Forces so strong that they defy our understanding and open the door to new realms of physics. While black holes may seem like cosmic monsters, they are a natural consequence of the universe's laws of gravity and thermodynamics. Their formation provides vital clues about the nature of matter, energy, and the boundaries of our physical universe. In many ways, the birth of a black hole is as much a beginning as it is an end. These objects not only reshape the space around them, but also have a profound influence on the galaxies in which they form, potentially affecting the formation of stars and the evolution of cosmic structures. The birth of a black hole is the final, irreversible step in the life of a massive star, where the core collapses into a singularity, creating a point of no return. It's a reminder that even in the universe, nothing lasts forever, and that even the most luminous stars can meet an incredibly dark end. Black holes come in a variety of sizes and masses, and though their basic nature is the same, regions of space where gravity is so strong that nothing can escape, their formation and characteristics vary depending on their type. Understanding the different types of black holes helps us unravel the complexities of the universe and the profound influence these mysterious objects exert on their surroundings. The two most well-known types of black holes are stellar black holes and supermassive black holes. each with unique properties and origins. However, there are still significant mysteries, especially when it comes to the formation of the most massive black holes in the universe. Stellar black holes are the most common type of black hole in the universe. They form from the remnants of massive stars that have gone supernova. When a star at least 8 times the mass of our sun reaches the end of its life, it can no longer support itself against the force of gravity, and its core collapses, forming a black hole. These stellar black holes typically have masses between 3 and 10 times that of the sun. Despite being relatively small on a cosmic scale, their gravitational pull is immense. Stellar black holes are scattered throughout galaxies, often hidden within star systems. In some cases, they are part of binary systems, where they interact with a companion star. As the black hole pulls material from its companion, the infalling gas forms an accretion disk, which heats up and emits X-rays and other high-energy radiation. This is how astronomers often detect stellar black holes, by observing the radiation from the material being devoured by the black hole. The most famous example of a stellar black hole is Cygnus X1d, and one of the first black hole candidates ever discovered. They are thought to power quasars. The extremely bright, energetic centers of distant galaxies, where the intense gravitational pull of the black hole fuels the release of enormous amounts of energy. The accretion disks around supermassive black holes and quasars can outshine entire galaxies, and their jets can span millions of light years into space. Despite knowing that supermassive black holes exist, their origin remains one of the greatest unsolved puzzles in modern astrophysics. How did these gigantic objects come into existence? Did they grow from smaller black holes that merged over billions of years? Or were they born directly from the collapse of enormous gas clouds in the early universe? This question is particularly perplexing because some supermassive black holes appear to have formed very early in the history of the universe, only a few 100 million years after the Big Bang. Given their massive size, it's challenging to explain how they could have grown so large so quickly. One hypothesis is that supermassive black holes could have formed from seed black holes. Smaller black holes formed from the collapse of the first generation of stars or massive gas clouds in the early universe. Over time, these seed black holes may have rapidly grown by merging with other black holes and accreting large amounts of gas. Another possibility is that supermassive black holes formed from the direct collapse of extremely massive primordial gas clouds, bypassing the need for a star altogether. Both theories are still under investigation, and ongoing observations using telescopes uncover more clues about these enigmatic giants. While stellar and supermassive black holes are the most well-known, there are other theoretical types of black holes that may exist. Intermediate mass black holes are thought to be the missing link between stellar and supermassive black holes. These black holes, with masses ranging from hundreds to thousands of solar masses, could form in dense star clusters or from the mergers of smaller black holes. While evidence for their existence is growing, intermediate mass black holes are much harder to detect than their larger or smaller counterparts. There is also speculation about the existence of primordial black holes, which may have formed in the very early universe, not from stars, but from the extreme density fluctuations that occurred shortly after the Big Bang. These black holes would have very small masses, possibly as small as a single asteroid, but they could still have a profound effect on their surroundings. Some researchers even hypothesize that primordial black holes could make up a portion of the universe's dark matter, but this idea remains highly speculative. The diversity of black holes, from stellar to supermassive and beyond, illustrates the complexity of these cosmic objects. Each type of black hole provides critical insights into the life cycles of stars, the evolution of galaxies, and the fundamental nature of the universe itself. However, its presence is undeniable due to the way it influences nearby stars and matter, as well as the incredible discovery of imaging the surrounding environment of this galactic monster. This disk can emit intense X-rays and other forms of radiation before the material crosses the event horizon and is lost forever. While we cannot see the black hole itself, we can detect the radiation from the hot material in its accretion disk, providing a fingerprint of the black hole's presence. Successfully capturing an image of our galaxy's own supermassive black hole would be a monumental achievement in astronomy, allowing us to better understand how these colossal objects behave, grow, and interact with their surroundings. The image of the black hole in M87 which is about 55 million light years away, relativity, and provided a visual glimpse of one of the universe's most enigmatic objects. So these celestial objects offer us a unique window into the limits of our knowledge, challenging our understanding of physics and presenting questions that remain unanswered. By their very nature, black holes defy the conventional rules of the universe. They warp space-time, slow down time near their event horizons, and consume everything that crosses their threshold. They are both destructive and creative, shaping galaxies while hiding the secrets of the cosmos deep within their event horizons. What makes black holes particularly fascinating is what they teach us about the very fabric of reality. As we study them, we begin to grasp the delicate balance between space and time, the interplay between matter and energy, and the extraordinary forces that govern the universe. Black holes reveal the extreme effects of gravity, showing us how space can curve, how time can slow, and how even light can be trapped. These insights not only expand our understanding of astrophysics, but also raise profound philosophical questions about the nature of existence. What lies beyond the event horizon? Could black holes be gateways to other dimensions, or are they simply cosmic endpoints? Each discovery we make brings us one step closer to answering these mind-bending questions. Searching. I've heard there are for nonce.